Some of the strongest welds in the world are created by a process you can barely see. No bright arc flashing in front of the operator, no shower of sparks flying across the workshop, no constant crackling sound that most people associate with welding. Instead, the entire welding operation happens beneath a blanket of granular material, completely hidden from view. Yet beneath that layer, one of the most productive and powerful welding processes ever developed is hard at work. It's called submerged arc welding, or SAW. This remarkable welding method can produce deep weld penetration, exceptional weld quality, and metal deposition rates that many other welding processes simply cannot match. In fact, when manufacturers need to weld massive pressure vessels, construct giant ships, fabricate railway components, or join thick steel plates with incredible efficiency, submerged arc welding is often one of their first choices. But how can a welding process work when the arc itself is buried under a layer of flux? Why would engineers intentionally hide the welding arc from sight? And how does this unusual process create some of the strongest and cleanest welds in heavy industry? In today's video, we're diving deep into the world of submerged arc welding. We'll explore what SAW is, where it's used, the equipment that makes it possible, how the process works step by step. By the end of this video, you'll understand why submerged arc welding remains one of the most efficient welding technologies used in modern manufacturing. Let's get started.
What is submerged arc welding? Submerged arc welding, commonly known as SAW, is an arc welding process that creates a weld by forming an electric arc between a continuously fed consumable electrode and the workpiece. At first glance, that may sound similar to MIG welding, but here's where things become very different. Instead of exposing the arc directly to the atmosphere, SAW completely covers the welding area with a thick blanket of granular flux. This layer of flux hides the arc from view and performs several critical functions during welding. The flux shields the molten weld pool from contamination, stabilizes the welding process, and can even introduce alloying elements that improve the weld's properties. As welding progresses, the arc remains submerged beneath the flux layer, which is where the process gets its name. The result is a highly efficient welding method capable of producing deep penetration, smooth weld beads, and extremely high deposition rates. In fact, few welding processes can compete with SAW when it comes to productivity. The history behind submerged arc welding. Submerged arc welding isn't a new technology. In fact, it has been around for nearly a century. The first patent for the process was issued in 1935 and involved creating an electric arc beneath a layer of granular flux. The technology was originally developed by Jones, Kennedy, and Rothermund. At the time, industries were searching for ways to improve welding speed, consistency, and quality. Submerged arc welding quickly gained attention because it solved many of the challenges associated with traditional welding methods. Today, it remains a vital process in heavy manufacturing industries around the world. Why is it called submerged arc welding? The name itself explains the process perfectly. In conventional arc welding, the arc is visible. You can see the bright light, sparks, and molten metal as welding takes place. In submerged arc welding, however, the arc is buried beneath a thick layer of granular flux. The arc becomes completely submerged and hidden from view. This unique characteristic creates several benefits, including reduced spatter, minimal arc radiation exposure, and excellent weld protection. It's one of the defining features that separates SAW from other welding processes. Where is submerged arc welding used? One reason SAW remains popular is its versatility in industrial applications. It is especially useful when large amounts of metal need to be welded quickly and consistently. Let's look at some of the industries that rely heavily on this process. Pressure vessel manufacturing. Pressure vessels operate under extreme internal pressures. Any welding defect can lead to serious safety risks. Because SAW produces strong and reliable welds, it is widely used in the fabrication of boilers, pressure tanks, industrial vessels, and chemical processing equipment. The process provides excellent penetration and consistent weld quality. Shipbuilding industry. Modern ships require thousands of feet of welded joints.
Many of these welds involve thick steel sections. Submerged arc welding is ideal for creating long, straight welds quickly and efficiently. Its high deposition rate helps shipbuilders reduce production time while maintaining structural integrity. Structural steel fabrication. Large buildings, bridges, power plants, and industrial facilities often contain massive steel components. SAW is commonly used to weld these structures because it offers deep penetration, high productivity, and strong joints. This makes it especially attractive for large-scale projects. Railway industry. Railway equipment demands durable and dependable welds. The deep penetration achieved by SAW helps ensure strong connections in rail-related components. This makes it a valuable process in railway manufacturing and maintenance. Automotive and military manufacturing. In applications where productivity and consistency are essential, SAW provides manufacturers with a fast and reliable welding solution. Both single-pass and multi-pass welds can be performed depending on material thickness. Stainless steel and alloy fabrication. Although commonly associated with carbon steel, SAW is also used on stainless steels, low alloy steels, nickel-based alloys. This expands its usefulness across multiple industries. Understanding the major components of an SAW system. To truly understand how submerged arc welding works, we need to examine the equipment involved. Each component plays a critical role in the process. 1. Wire electrode. The wire electrode acts as both the electrode and filler metal. Unlike stick welding, where electrodes must be replaced frequently, SAW uses a continuously fed wire. This allows uninterrupted welding for long periods. The wire typically ranges between 1.6 millimeters and 6 millimeters in diameter. Depending on the application, it may be solid wire, cored wire, twisted wire, or tubular wire. Some advanced systems even use multiple wire electrodes simultaneously. This dramatically increases deposition rates and productivity. 2. Flux. Flux is one of the most important elements of the SAW process. Without flux, submerged arc welding wouldn't exist. The granular flux covers the arc and weld pool completely. Its responsibilities include protecting the weld from atmospheric contamination, stabilizing the arc, refining the weld metal, influencing weld chemistry, and controlling bead shape. As welding progresses, part of the flux melts and forms protective slack. Unmelted flux can often be recovered and reused. Types of flux used in SAW. Several types of flux are used depending on welding requirements. Granular flux is the most common. It contains compounds such as aluminum oxides, calcium oxides, magnesium oxides, manganese compounds, and silicon compounds. These ingredients help control the welding process.
Bonded flux. Bonded flux is manufactured by mixing ingredients and baking them together. It offers flexibility and allows the inclusion of alloying elements. Fused flux is produced by melting ingredients together in an electric furnace. The result is a highly consistent flux composition. This helps maintain uniform weld quality. 3. Power source. Like all arc welding processes, SAW requires electrical power. The power source generates the energy necessary to create the arc. Different power configurations can influence penetration depth, bead profile, deposition rate, and arc stability. Many systems utilize AC, DC, or combinations of both depending on the application. 4. Flux hopper. The flux hopper stores and delivers flux to the welding zone. As welding progresses, it continuously feeds fresh flux ahead of the arc. This ensures the arc remains fully submerged throughout the operation. 5. Welding head. The welding head directs both the electrode and flux toward the joint. In automated systems, the welding head moves at a carefully controlled speed. This ensures consistent weld quality over long distances. How does submerged arc welding work?
Now let's explore the process itself, step by step. This is where all the equipment comes together. Step 1. Joint preparation. The workpieces are positioned and aligned properly. Since SAW is commonly used on thick materials, proper joint preparation is essential for achieving complete penetration. The welding equipment is then positioned along the joint. Step 2. Flux application. Before welding begins, granular flux is deposited over the welding area. This creates the protective blanket that will cover the arc. The flux layer must be thick enough to completely shield the welding zone. Step 3. Arc initiation. When power is applied, an electric arc forms between the wire electrode and the workpiece. Unlike conventional welding processes, this arc immediately becomes buried beneath the flux layer. The operator cannot directly see the arc.
Step 4. Flux melting. The intense heat generated by the arc melts part of the surrounding flux. As the flux melts, it forms a layer of molten slag above the weld pool. This molten slag provides additional protection and insulation. Step 5. Metal melting. The heat from the arc melts the wire electrode, the edges of the base metal, and the molten metal combines to form a weld pool. Because the process generates substantial heat, deep penetration is achieved. This is one reason SAW performs so well on thick materials. Step 6. Weld pool formation. The molten weld pool travels behind the arc as the welding head moves forward. The slag layer continues protecting the molten metal from atmospheric contamination. This protection helps reduce defects and improves weld quality. Step 7. Solidification. As the weld cools, the molten metal solidifies into a strong joint. The molten slag also cools and forms a protective layer on top of the weld bead. This slag is later removed during post-weld cleanup. Why does SAW produce such high deposition rates? One of the biggest advantages of submerged arc welding is its incredible productivity. But why is it so fast? Several factors contribute. First, the continuously fed wire eliminates frequent stops. Second, the flux blanket allows higher welding currents without excessive spatter. Third, automated systems maintain consistent travel speeds. Together, these factors allow SAW to deposit far more weld metal per hour than many conventional welding methods. This is why large manufacturing facilities often rely on SAW when productivity is critical.
Conclusion. Submerged arc welding may hide its arc beneath a blanket of flux, but there's nothing hidden about its impact on modern manufacturing. By combining a continuously fed wire electrode, a protective flux blanket, and powerful automated systems, SAW delivers some of the highest deposition rates and deepest weld penetrations available in industrial welding. From shipyards and pressure vessel fabrication shops to rail car manufacturing and structural steel construction, this process continues to prove why it remains one of the most productive welding methods ever developed. Its ability to create strong, high-quality welds with minimal spatter and excellent consistency has made it a cornerstone of heavy fabrication for decades. While it may not be suitable for every welding position or material, when it comes to joining thick steel efficiently and reliably, few processes can compete. And now, the next time you hear the term submerged arc welding, you'll know exactly what's happening beneath that blanket of flux and why industries around the world continue to depend on it. If you enjoyed this video, don't forget to like, subscribe, and turn on notifications for more in-depth explanations of welding technologies, fabrication techniques, and industrial engineering processes. Thanks for watching, and we'll see you in the next video.